before I get to the material for section 2.4, I need to introduce a sneak peek. This is a derivative formula that we will be proving in chapter 3, but it shows up already in the examples for the slides that I'm using. So just so we know what's going on, if we have to take the derivative of the exponential function, so here I've got d on dx applied to e to the power x, that derivative is also just going to be e to the x. The exponential function is its own derivative. Again, it takes a little bit of work to prove this, and that work will be coming in the future. But for right now, let's go ahead and use this relation as long as we're doing the slide examples. So taking derivatives using this rule isn't so bad. If I wanted to calculate the derivative of f of x equals e to the power x minus x, then I know I can break this expression down. I'll call this, well, I need to take the derivative of e to the x. I need to take the derivative of x, and I am subtracting those two derivatives, the one from the other. So here, my first derivative, f prime of x, is equal to e to the power of x minus 1. And if I wanted to go further and compute the second derivative is just the derivative of the first derivative. F double prime of x is equal to d on dx applied to the quantity e to the power x minus 1. Again, I can break that down and say that this is d on dx applied to e to the x minus d on dx applied to 1. So this is the derivative of e to the power x minus the derivative of the constant 1. Constants have 0 as their derivative, and the exponential function has itself as its derivative. So my f double prime here would be e to the power x. Now, intuitively, what's going on here in my picture, we've got the f, the original function, in blue, and f prime graphed in pink. So just like before, I can look for tangent lines. Here I see that I'd have a horizontal tangent line where I've placed my mouse, and that is exactly the x-coordinate where f prime is equal to 0. Now, for negative values of x, my original function is decreasing, and I see that represented because the derivative is negative in those places. Negative slope indicates a decreasing function. For positive values of x, my original function is increasing. An increasing function must have a positive slope, and I do see that my derivative is positive in those places. So my derivative is telling me all of that geometrical information. For right now, we're going to use this formula just as sort of a black box, and only with dealing with the problems on the rest of the slides for this lecture. Again, we'll be revisiting this exponential formula in about a week's time, maybe a week and a half, and actually proving why this is the case it is.